Okay, mic test, mic test. Okay, so so hi everyone. This is the first talk of this year, and I'll be talking briefly about okay, fine, of this semester, and sorry, my year starts at August, right after summer. Okay, so yeah, I'll just briefly go through some slides that it's sorry, it's a kind of scuffed because I rushed this over the weekend for an interview, so. Yeah, so this is my rehearsal for the interview, kind of. So, okay, so
Which company, by the way, you want to share?
let me just pull out my here. Okay, so here's a rough overview of what I'll be covering. If you are a freshie, then the first few parts will be more relevant for you because I'll be introducing like what a web server does in the background. And then after that, if you are not a freshie, if you're a bit more well versed with the Linux kernel, then the later parts might be more interesting to you. So I hope to cover a wide range of skills. Okay, so usually how I recommend people study kernel networking is I tell them the best way is to write a web server in C, and then from there you trace the syscalls. So yeah, so usually how I do it is I recommend just telling AI to do it. So in this case, I just told Cursor to write a web server in C, and then you see that this is a web server in C, and this is me testing the web server. So I compile the web server, I run a.out, and I open a browser, and I go to localhost 8080, and we see that it does appear. So this is the bare bones you need for a web server in C. At any time, if you guys feel like asking questions, feel free to just interject. So from there, if you write the web server in C, you'll see that there's a lot of system calls. So things like read over here and write over here, there's a whole bunch of them. And to understand how the Linux networking works, I think a good place to start would be tracing all the system calls and understanding what each of them does. So that's what I'll be doing for the first 1/3 of this talk. So yeah, so the first syscall that is important is socket. So okay, along the way, right, there will be a few words here that I highlighted that I feel are especially important if you want to study for interviews. So these are like the theoretical minimum for passing a maybe like interview. So yeah, just to place emphasis on those. So the socket syscall, what it does is you can see over here in the socket syscall you pass in something called the address family and something called the IP, like the IP, is it IP? No, I think it's the TCP part of the layer 4, I think. But basically you pass in two parameters here. This is the IP and this is the TCP. So yeah, so AFINet in this case represents IPv4, which basically means that you're going to bind this socket to IPv4 address, and sock stream is representing TCP, which means that you're going to be sending information via the TCP protocol. So so some other options you can pass in is like AF Unix. AF Unix is a Unix domain socket. So if you ever use Docker and you realize there's a /var/run/docker sock, right? That's a AF Unix socket. And there's also another one which is AF local, which
So what is an AF unit socket?
so if it's an AF Unix socket.
No, what is an AF unit socket?
The AF basically, later on when we trace what happens when we send data to a socket, basically this is kind of like the implementation of how the socket behave. So if you
like a traditional HTTP socket. We're not talking about web sockets here, right? It's like a one call, one response thing.
Web sockets is built on top of TCP, so this includes that.
Okay, so you can handle both web sockets and normal.
Yeah. Web sockets, wait, correct me if I'm wrong, web socket is built on TCP, right? Yes, right? I think so.
I believe so, yeah.
So this is currently what I'm showing here is a TCP IPv4 socket. And basically, so your question is what does AF Unix bind to, is it?
Yeah. What is an AX Unix?
Okay, so maybe if I just so that's a good question.
Is it a Unix domain socket?
Yeah, it's a Unix domain socket. So if we see, I'm not sure if so have you ever seen like have you ever seen the thing, something like Have you ever seen something like, if you run Docker locally, right? Have you ever seen like var run docker.sock? Something.
Usually Docker is like abstracted away, like you just click a button and it runs. Like,
Yeah. But like if you use Docker, right, this is one of the sockets that are created. So this is an example of an AF Unix socket. It's like a file that exists locally that you can read and write to. It kind of behaves like a queue of sorts. So let's say I have one application, right? Let's say I have two processors on the same host.
Okay.
They can communicate via one of these like AF Unix sockets.
So like a channel.
Yeah, kind of.
Okay.
Yeah, so I think this is the best example I can give for AF Unix socket. Yeah. So imagine, right? Let's say you are a program. Let's say you are a process, and then there is and then you create a AF iNet socket, right? If you send data to AF iNet socket, it will essentially send data via IPv4 to other people.
Okay.
But if you create an AF Unix socket, and let's say somebody else connects to the AF Unix socket, then if you send data to it, it does not go out to the internet. It gets routed like locally to the other process.
So it's like a local routing versus a internet routing.
Yeah, but from my process point of view, right, I just see a socket. In both cases, I'm writing to a socket. So what happens after I write to the socket is handled by the operating system differently.
So that's where the Unix operating system comes in. Is how it handles those sockets.
Yeah. So basically correct. So basically the AF Unix here, the address family here is kind of like a setting that you can tell the kernel like, hey, when I send you data, what do I want you to do with it? Do I want you to send it via IPv4 or send it via IPv6 or send it via local Unix thing? Yeah, so this is kind of like a setting that you can choose for the socket. There's many types of sockets. So there's also like one for AF Bluetooth apparently. So like Bluetooth, if you create a Bluetooth socket, then you imagine that you'll be connecting to some Bluetooth devices, and you send data to that Bluetooth socket, you'll go to that Bluetooth device.
Okay, so this socket is basically you call this thing and then you tell it what you want it to do, and it will like process the data how you want it to essentially.
Yeah.
Okay.
Yeah. So so this is Linux kernel networking works via sockets in general, and I think this applies to Windows as well, although they might call it maybe something a bit different. If anyone can weigh in, just feel free to shout out. Yeah. So what does this syscall return? This syscall returns a number. You see this case, socket returns a integer, and it returns basically a number. And so this server socket is what we call a file descriptor. So right now in this program, server socket will be 3, right? Because 0, 1, and 2 are file descriptors for input, output, and error. So so this is how you create a socket. So that's the first syscall that is involved when you create a web server in C. Any questions? Okay, thanks for the questions. Yeah, so the next thing that you do, so this is all output from the AI, and I'm just analyzing it and understanding it. So the next thing that you do is now you have a socket, and from your program's point of view, it's just an integer, right? It's just a file descriptor. So the next thing that you do is you bind the socket to an address, right? So if you've ever done a bit of web development, you might have done something called like dash like host 0.0.0.0 or bind to 0.0.0.0, and this might fix some of your hosting issues. Like if you bind to like localhost 127.0.0.1, it might not be accessible from other devices on the same network. But if you bind to 0.0.0.0, like other devices on the same network can suddenly access it. So this is what we mean by binding. So essentially, so in this case you bind to in this case, because our socket is an AF iNet socket, right? It's an IPv4 socket. We need to bind to an IPv4 address. If your socket was IPv6, then you bind to an IPv6 address. And I imagine that 50% sure on this next sentence, but I imagine that if it's an AF Unix socket, then you bind to a found path probably. So this is how you bind to address, and from then you're now like serving. You're now accepting. Wait, sorry, you're not exactly accepting connection, but this is one step of the process.
So binding is modifying the socket you just created.
The socket itself is just right now, as of now, it's just a file that doesn't really do anything. So binding is saying that, hey, I want to bind this socket to an address so that other people, when they connect to this network, connect to the network interface card, the data will appear in the socket. So binding, so you have a socket, it's kind of like let me think of a good analogy. a socket is kind of like okay, I guess like a socket is kind of like a receptionist. Then like by binding, you're kind of like open the doors, the entrance like that, like saying like, okay, that's my best analogy. If anyone has anything better, feel free to shoot.
In the sense that the doors is all the network interface card on the
Yeah.
computer, right? So basically,
Yeah.
if you open the door, right, means that the socket is listening for all the traffic on the that's
Yeah.
going through the network interface card. So there's some network interface card that's like maybe like open to other machines on the network. That's why other machines can basically like reach the location.
Yeah, that's right.
So if you create a socket and you don't bind it, it's
Not accessible.
useless basically.
Yeah, it's
Okay.
useless. So you need to bind. Yeah, correct. The socket is just sitting there, but only if you bind it, you're exposing it to other people.
It's like opening the doors basically.
Yeah.
Okay, that makes sense.
Yeah. So that's good questions. So keep them coming. Yeah. So yeah. So at a very okay. So then this is the next part of the code. So after you bind a socket, you do something called listen, where basically now you're listening for connections, and then now you do something in the while loop. You keep on accepting. You keep on calling accept syscall over here, and basically accepting the accept syscall will accept new connections on this socket, right, which is bound to the IPv4 address, and every new this part is quite interesting. Every new connection that comes, it will actually spin up a new socket called a client socket. So right now server socket is like 3, right? Later I'll have a step through of like some animation to step through this, but right now server socket is like 3. And when you call accept, let's say 2 new clients come in, then the 2 new client sockets created will be 4 and 5. So this is, I believe this is what they call TCP multiplexing. So yeah, so so once you accept a new client.
Do you have a reasoning why we do TCP multiplexing? Like why does it want to spin out a new instance of the socket?
Because I think it's a easy way to kind of allow. Wait, let's say it's an easy way to keep track of how many of all your clients basically. It's an easy way to keep track of this client is who, and like so each client is assigned some socket, so that if I want to send data to one client, I can just write to that socket. Instead of saying like if there's only one socket, right? Imagine there's only one client socket for all the clients. Then when I send data to them, I need to specify a way of like saying hey, I send data, but I want it to go to this guy. So that you need to tie some metadata to the thing that you send to the socket, which can get, I mean, it's theoretically possible probably, but Linux chose to do it this way because it's very neat. It's like each client is its own socket, and it closes the connection. Because TCP is also stateful, right? So you need to maintain like, oh, this client is connected, this disconnected, this has like sent 5 SYN requests, but I haven't replied, things like that. So it's just
like a
better bookkeeping.
Okay.
Yeah. And then from here you call handle client on the client socket, which is a function that will read and write to the socket later on. And lastly, after you exit the while loop, right? After all the clients have after you exit the while loop, you close the server socket, and closing is important to free resources. Yeah. So this is the bulk of the handle client, and basically what's happening over here is that when I have a new client, I read from the client. Right? I read from the client here. I read from the socket, and then I can process some data that the client send me. Maybe they send like get some index.html, or like they send some web like form data. I can process it. But in this case, I'm not doing anything fancy with it. You see, I'm not using buffer. But after you process the user data, you send right to the client socket to respond to it. And that's the key idea. So you see that the read and write, right? They're writing to this client socket, and this client socket is actually just a number. It's just a file descriptor. So it's the way you read and write to a client socket is exactly the same way you read and write to a file, right? If you want to read or write to a file to save like some data on the local disk, it's exactly the same thing from the file descriptor point of view. So you see that all this is abstracted away. Like a whole network connection to a client is a file, and writing to a file is also a file, and there's a lot of other instances of this in the Linux kernel. So that's the idea where everything is a file, and this is just a way that Linux kind of chose to do this. It's a design decision that Linux made. So this is what they mean when they say everything is a file. Okay, so if that was a bit too much code, here's some animation that I spent a bit too much time on instead of reading the Linux kernel source code. So when you create a socket, right? Imagine the cat is an application, and he's calling the syscall socket, AFINet and sockstream, and 0 just means default like settings kind of. And so the Linux kernel will will listen to the syscall and return a file descriptor. In this case, it's 3. And the Linux kernel will create the socket internally in its own data structures and all that. Then now they bind, right? So now the web server binds to this address and this port. Semantically is this, but of course in code you actually put it in a struct and all that. So this is just a bit of a more like semantic, closer to the semantics. And then once you return success, we know that it's bound. And then so now when you listen, you pass in the file descriptor, right? And then you pass in a parameter, a number which represents how many connections he's willing to serve simultaneously. And so so now you're in the while loop, and now you're accepting on that file descriptor tree. And in this case, because there's no clients yet, what happened is that this syscall will block. So from the process point of view, it gets stuck over there, and the process goes to sleep. The code after it does not run yet, and it just blocks and it just goes to sleep. And so if the kernel will probably schedule it off and let some other process run on it before waking this guy up when a new connection comes. So let's say a client comes, and so right now he's just sleeping, waiting for a new client to come. So the kernel will tell him to go to queue, and then the kernel now will wake up the application. And so now he'll wake up and he'll be like, okay, let me serve this new client. And so now, right, remember he went to sleep when he called the accept syscall. He went to sleep basically around here, right? And now the program will resume. So from the client, this code point of view, right, it's as if they are kind of like, they don't know that they went to sleep, right? They just called this and they.
It's as good as saying like await for a connection.
Yeah, basically await. Yeah. So it's as good as saying await. And so now he wakes up over here and he gets assigned the client socket returns. It gets assigned a value of 4. And so now using 4, right? So now this is the client, and now using 4, they can read and write to it as they wish. So if you read from it, you might get something like get index.html. That sounds like it could be part of a HTTP string. And then after that, you process it and you write to it, and then he can send him this whole thing, which is part of the response. And lastly, after that, he close. So that
after this close, right, does it not like wait for another connection? So like if you write it like this, means you can only serve once.
So right now, as of now, if you call get index.html to this server, it'll respond to you, and then the client connection is closed. So if you initiate a new connection, it'll be a fresh new connection.
So you'll run this code again automatically?
Yeah.
Okay,
Yeah.
so you can infinitely make as many connection requests as you want. So it's like a live server essentially.
Yeah.
Okay.
And what's interesting over here is that if you guys have heard of the idea of long polling or like WebSockets, I believe it's something similar here. Basically, the idea of, correct me if I'm wrong, but the idea of long polling / WebSockets, they're closely similar, but the idea is that you open a connection, the client opens a connection, but they do not, the web server does not close it so soon. It does not like just answer one time and then write one time and close. So it keeps the connection open. So now the server will keep track of all these many file descriptors that they have. And then, but this like highway of information is still open for back and forth. And only way later when you decide that you don't want the connection anymore, then you close it. So that's the idea behind long polling and WebSockets. Yeah. So it's still built on TCP, just that it's as if like you can pretend like there's streaming kind of. Yeah. So yeah, that's I think that's an interesting parallel to draw. So now that handle client is over, he goes back to the while loop again, and he's calling accept, waiting for new clients again, and he'll go to sleep again, once again, and yeah. So question is, okay, so.
So this current setup, you can only serve one client at one time.
Correct.
Okay.
Exactly. So I'll show a multi-threaded version later. So question is, what if there's too many clients? So actually, okay, I'll show this slide because this queue over here is a bit simplified. I believe this is the accept queue. Yeah, this is the accept queue over here. But there's actually another queue that the operating system maintains called the syn queue. So it's actually two queues at play, like because TCP is stateful, so you send syn ec and then syn ack and then ack, right? So there is a queue for clients who have sent SYN to you, but you haven't sent SYNEC back. Yeah, there's a queue for that as well. So this block, I think, is quite a good read. I think it's quite a good read, if I remember correctly. Okay, yeah. So back to the question. Yeah, okay. So let's say this client right now is serving one client, and so because we are in a single threaded program, he cannot really call accept on other stuff. So he's busy serving the client, and maybe the client is like taking damn long. Maybe he sent a lot of data, right? Maybe he's a malicious client who sent a huge file. Hold on. Let me just pick this real quick, cause hello. Okay, it's a scam call. Sorry. Cause I have a meeting later at 11, so I was not sure if that was like HR or something. Yeah. So let's say while he's serving client 5, right? Like many other people come along, and basically once you reach the end of the size of the accept queue, the beyond that the connection gets dropped. So this is a very sad client because his connection gets dropped. Why do they keep calling me? Okay. Yeah. So question: how do you solve this? What if you want like malicious client over there that takes very long, and then you don't want to be blocked by that guy, right? So that's where multi-threaded web server comes in. So the idea is that you can, if I just told Cursor to make this server multi-threaded, you can see that what it did is it changed handle client, right, from that line of code to something pthread, and then it calls pthread create. So it creates a thread, right? Pthread is POSIX threads, and it creates a POSIX thread, and it passes in the function pointer handle client to basically give the pthread this function to run, passing in the parameter client sock as well, and so from here, and so basically it creates a new thread.
Actually, I got an interesting question for you. So while let's say if I connect to the web server and I send it a lot of data, right?
Yeah.
So while the server is receiving data, that is an I/O operation, right? It doesn't actually use any CPU.
Exactly.
So is it able to run on this thread while collecting data from a particular client?
So the question is, since it's I/O, is it able to run on?
Well, is it able to run another thread, like another connection? Let's say you implement it like this, right? And then the first guy, it sends like a 2 terabyte piece of data, and then you're waiting for that data to come in. Are you able to run another thread to accept another connection?
Yes. So if you have multiple cores, so one thread will be busy with that. But then let's say I have 48 cores, let's say, then the other 47 threads can tend to other 47 other connections. But if I have like 50 malicious clients who send very big files, then in that case they'll be busy. It might get.
But you can create infinitely many threads, right? There's no like limit on.
Yes, but like the maximum parallel processing is the number of cores.
Yeah, I think also creating threads come with like overhead. Like basically like have metadata to manage the thread. Actually, I think is that maybe you can have some sort of like event loop also.
Yeah.
Just have one thread, but it's asynchronized. So
That's
it's
right.
not blocking itself. So it's when there's IO bounded, right? You can go and process the next incoming request. Then when the IO operation finish, right, you can basically use the event loop to tell the thread to process the.
It's like force your way in and then you can run again, right? Yeah.
That's right. So I think one thing I'll say is that it's not true that if you create infinitely many, like if you create 10,000 threads versus let's say 50 threads, usually you'll find that the throughput, if you have let's say only 40 cores, right, you find that between 50 threads and 1,000 threads, the throughput is around the same because you're more or less limited by the number of cores. So just creating more threads doesn't necessarily mean that you get more parallel. It really bounds down to like number of cores because what's running the threads are the cores.
Right.
Yeah.
No, but as in when it's blocked by I/O, the thread isn't actually running, right? We're just waiting for external operation to complete.
Yeah, that's true also.
Yeah, and it doesn't like in this case you're just returning some data from the backend. So I don't presume like that's going to take a lot of processing.
Yeah.
It's like it's only if you're downloading a lot of data.
Yeah. Okay. Yeah, great. So so one popular interview question is what's the difference between process and threads? And while it's not exactly relevant here, I think if you don't know the answer to this question, it's good to go and look it up. So what it looks like from this diagram is that every time a new connection comes in, he'll tend to each client by dispatching a new thread. So yeah, that's what I mean by multi-threaded web server. And so there's actually a lot more design space over here. I think these are some keywords you can look up: async IO and event loop. Basically, it gets quite complicated. So just now it's multi-threaded, but what if read and write, even if it's multi-threaded, the thread itself can, if it calls read and write, it will get blocked, which means that you need to have a context switch and all that. So what if we don't really want, what if we don't want a blocking syscall? Then you can use, there are certain settings you can tune to tell the kernel, I don't want you to block me if there's no data. So that kind of moves the scheduling of the I/O stuff and polling from the kernel's responsibility to the user's responsibility. So it's kind of like a very high level overview, right? All these advanced settings, they kind of allow you to tell the kernel, like, hey, I know you have all your code that is ready to handle all my fancy blocking logic and I/O, but if you tune these settings on, you're kind of telling the kernel, I know what I'm doing, I wrote something that's better than what you have, let me handle it. And then the kernel will be like, okay, sure, if you want to handle it, then read is no longer blocking. You can now, read and write is no longer blocking, and I assume you know what you're doing. And so basically, if you're a good programmer, you write user space programs that handle all this very well. Maybe you are the author of Node.js libuv, or maybe the author of Tokyo, and you're telling the kernel, like, I know what I'm doing, just let me handle these advanced settings. So yeah, I think interesting, maybe an interview question that can show up is what is PO and EPO, which basically allows you to, right now you're reading and writing on one file descriptor, but PO and EPO kind of allows you to say, like, I put all this bunch of file descriptors into a collection, and then you tell the kernel, I'm going to read, as long as you can read from any one of those, inform me. So maybe PO will like block until as long as one of them. So it's like, if any of these file descriptors give me a message, let me know. So it kind of allows you to multiplex connections. Yeah, it's called multiplexing basically. EPO is a bit more efficient. I think it came out in the 2022. I'm pretty sure it's 2012. Introduced in Linux 2.5.44. Yeah. So EPO is some newer technology, and IO Uring is also a new technology that basically I would not elaborate too much on it, but basically allows you to have very little syscalls by kind of like batching certain, kind of like batching like data. So you write it to a ring buffer. There's like two buffers or something, and then you write it to those buffers, and then you call the syscall to like inform the kernel that you have written to it. Yeah, if anyone like Gerard might have any comments on IO Uring, feel free to.
It's very unsafe. Don't use it.
Yeah. So IO Uring was it had a lot of bugs, a lot of security bugs. A lot of security people got very rich of it. Yeah. So yeah, so that's the basic like overview of how as a user you use the kernel networking API. And so now I'll give a brief dive into what the kernel code actually kind of looks like. So basically, okay, so when I approached this, after a while I found that like this is how I best learned the Linux kernel. So there's kind of like two parts to it. One is tracing the kernel code, which gives you like all the raw detail, right? The kernel code is the source of truth for all the stuff that you learn, all the conceptual stuff. So this is good to trace the kernel code because it's a source of truth. And so and things change over time as well. So resources you see online might be outdated. So you trace the kernel code. One thing you can do is you can say, what happens when I write to a file descriptor? Then you trace it all the way down until it hits the network interface card. So that's something that I'm going to do later. And another way is you learn all the data structure. So like, they say like when you're investigating financial crimes, follow the money, right? So in a similar parallel, if you're investigating the Linux kernel, follow the structs, right? You follow the data, follow the structs that you see, and see where they get passed around. So in this case, skbuff is a particularly interesting structure to follow because it represents a packet. So as a packet gets passed down the OSI model, you can see what subsystems kind of read and write to it. So you can see, oh, you're appending an IP header, you can appending the TCP header over here. And of course, thankfully we live in the age of ChatGPT. So whenever you see something you don't know, you can always ask AI. Yeah, but usually still use the code as a source of truth. And so that's the tracing kernel code. So conceptually, I think mainly finding whatever blogs you can find online and watching YouTube talks. That's how I usually learn. Okay, so so for read the structs, right? For follow the structs, here are some structs that are quite useful. So skbuff represents a packet, net device represents a NIC, socket represents a socket, and sock represents socket as well, but like I think this one is closer to user space, whereas this one is more like internal to the operating system. I think they have pointed to each other as well. So they are kind of basically conceptually similar. You can kind of, yeah, but just that one is more for user space and one is more for kernel space. And so here's kernel code. So I'm gonna pick out because I didn't really have a lot of time to make slides. So the following slides are literally just gonna be screenshots like that. So but I did have time to write out a very long list of what they do. So yeah, so along the way, I'll show this slide at the very end also, but along the way, there are a few patterns that you observe. So like C-style polymorphism, right, is, if you are familiar with languages in general, you know that like Java interfaces, right, and interfaces in general allows for polymorphism. So you can have multiple, if you have an animal interface, you can have a cat that extends it, you can have a dog that extends it, and how it works under the hood is just a V-table, right? There's a V-table with function pointers. So C-style polymorphism, there's no classes in C, but they emulate this by having a struct of function pointers, which they usually call like file operations, something like that. You'll see later.
This is polymorphism, but you write out the code for
Yeah.
how you would implement polymorphism.
Correct.
In C, basically.
So C-style polymorphism is literally, I write the V-table.
Okay.
Yeah. So you also see C-style inheritance. So right now, if you extend something, right, like dog extends animal, right, you realize that if you look at the address, it's like animal comes first, the data for animal comes first, and then like dog, and then like whatever is a subclass of dog. So basically, the way that the memory layer of each struct is handled in C++, for example, is something you see similar here, just that it's very explicit. Later you'll see comments that literally say like, this must be the first member of this struct, if not it will not work, because basically they do it like by hand. So that's also something interesting to see. And in general, for asynchronous behavior operations, is the most of the famous pattern you always see is queues and callbacks. So you see later that when I send data to a packet, it'll travel down the call chain, and then eventually it'll just write to a queue, right? And then at the other side, where the NIC driver itself would have it'll wake up by some interrupt calling it, and then it'll basically read from the queue and it'll send it out to the NIC. Yeah, and the last point is that there's a lot of interaction. So that you see function calling a function calling a function. The call stack is very, very, very big. So yeah, so without further ado, we start over here by seeing syscall define. So this defines the syscall. So if you want to start tracing, you always write something like syscall define. 3 is the number of parameters that write takes. So you might see 2 or 4 for other syscalls. And then you see that it just calls ksysWrite, which calls this function. And so ksysWrite, it gets a file. So you see that it gets a ksysWrite gets a file here. Okay, it gets a file. It gets a file here. Fd file of f. F is the file descriptor basically. Yeah, f is the file descriptor, and then you get a file from it, and you also get an offset. And yeah, so this refers to something called, how fd file works is something called the open. So you look at the file descriptor table, and then from there you'll get an open file table. So these are keywords you can look up as well. It's all part of the virtual file system. Yeah. Yeah. Then you see what it does is it calls VFS write on the fd file of f. And so what is VFS write? So VFS write, it calls new sync write. So you see that all the way down here, it does a bunch of checks. So right now you see the sort of conditionals that branch out into different areas, but I'm going to focus the main one that will probably typically happen. So if you probably call fsync a new sync write, and so new sync write looks something like that, and it'll get something called the IO kernel control block. Sorry, kernel IO control block, KIOCB. So this is something that is a unified interface for synchronous and asynchronous I/O. So basically, it's saying like it's kind of converting into this format so that it uses a common framework that handles both synchronous and asynchronous I/O. Yeah, and then from here, so it also calls the IOV iter, which stands for IO vector iterator, which basically is a way of just reading the user's data. So you'll call write iter. So this is the first interesting thing we see, right? We see that now we have a file pointer over here, flip, right? And it calls fop, file operations, and it calls write iter. So this is the first instance of a C-style polymorphism we see. And so so you see that the write iter over here depends very highly on what the file pointer is, right? Depends on what the file operations is. So if you have a socket file operations, then it behave a certain way. If you have a ext4 file operations, then it behave another way. So in this case, we got interested in socket. So yeah, so this is a struct of this is the V table I was referring to. A struct of all of our function pointers. And so from here, you see that for the socket file operations, we populate some of them with function pointers, and in this case we call sock write iter. So this is sock write iter. So that's the first instance of once again that's the first instance of C-style polymorphism we see. So a sock write iter, it gets a socket from the file private data. Here we see. So maybe questioning, how does a file store like a socket, right? And the answer is here. It stores it in this thing called private data. Basically, private data is an arena for like arbitrary data that your VFS, your virtual file system might want to support.
Is it just like binary, like this file?
Yeah. So this is like if you interpret this private data as another struct, you completely mess things up. So right now you got to make sure that you really like are very careful with what you read and how you interpret it. So that's why like C is very memory unsafe, because if you imagine like instead of socket here, you read like message header, then you're just screwed, like it's just corrupted. Yeah.
We can still read it as socket afterwards, right? Like just reading it doesn't corrupt.
Yeah, sure. But if you do operations on that message header, then things will be screwed. Yeah. So basically this private data is like just a void pointer buffer that just a chunk of data basically that without like some interpretation by itself is very hard, it's like meaningless. And so you need to just be careful how you read it, I guess. So that's the sock write iter. It creates message header which basically wraps the KIOCB and IOV iter. There's a lot of like terminologies here that will seem a bit obscure because after a while you just see the same names again and again, and it becomes like your best friends, right? So so now we go to send sock. Okay, so we see over here that it calls sock send message. So send message is actually a syscall as well. So it calls sock send message, which performs security checks, right? For SE Linux, if you heard of security enhanced Linux before this, where it comes in useful. And otherwise it calls sock send message no security, which means that I've already checked that one. I already checked the security, so you can just go ahead and assume there's no security check involved. And here we see another instance of C-style polymorphism, right, with the V table here. So it calls sock ops and send message. And in this case, basically ignore this one, right? It actually, for inet, it actually calls this guy. So right now what we're calling is inet send message. Yeah, so from there, and all the other stuff is just like instrumentation for observability and all that. So over here we see that there's a ops over there, right? Sock ops over here, send message. So send message, once again, is a C-style polymorphism. Send message is one function pointer. And for TCP protocol, send message is, surprise, TCP send message, right? And so TCP send message continues down the chain like that. So in this case, we see, there's a bit of synchronization over here with lock sock and release sock. And in between, you call TCP send message locked. And so what is TCP send message locked? It's a really, really, really big function that handles a few things. So it handles something called zero copy. It handles something called fast open. So these are all keywords that you can search up their features. But this is like where like all things so far we have seen is not really that meaty, right? Like this is the bulk of the TCP protocol essentially. So this handles zero copy, fast open. This also waits for the other socket to enter the established state. And it checks if the socket has been linked to a linked list of SK buffers. So basically, this one, okay, so right now, right, so far, the user's data is still hidden in message, right? We haven't like transformed the user data and attach it to, we haven't modified the user data much, haven't really touched it, just been passing it down. But at this point, you actually, from this point onwards, when you call the next thing, you actually do not pass down message header. So this is the function that processes message header, right? So how it processes it is, it will read the message header, and if you guys heard of TCP segmentation before, it'll read the message header, it'll split it up into MSS sized chunks, basically some fixed size chunks, maybe like 1500 bytes or something. It'll split, or 1400 bytes, it'll split it up fixed size chunks and then turn it into packets. So this is the first instance where we process the user's data and turn it into packets. And it'll append to a linked list of packets that will need to be sent by SOC. So actually after this, right, you're kind of taking this, turning a linked list and attaching it here. So now from then on, you only pass in the SOC. From now on, you only pass in SOC, and SOC will have a pointer to the linked list of messages, of packets. Make sense? So linked list is actually a very common data structure that's used in the Linux kernel because, if you don't need random indexing, if you're just sequentially accessing stuff, which is very common in kernel operations, linked list is the best guy for it. So,
isn't linked list like a common data structure in general?
okay, I guess so. But I guess like, yeah, I guess so lah. But it appears a lot in the kernel, so
I see.
yeah. Like I don't really think you see arrays much in the Linux kernel at all. Yeah. So it's unusually popular in the Linux kernel. Yeah. So oops. Yeah. So send. Okay, I was there. So TCP push it pushes the data. Yeah. So it just calls push pending frames basically. I think it does some stuff that are not. There's some TCP optimizations for if there's more data coming or if it's TCP urgent. So apparently those are features that TCP supports. The Linux kernel supports for TCP. But otherwise, it just calls push pending frames. And push pending frames, it'll ensure the TCP connection is still not closed yet, and then it'll call TCP write transmit. So this guy. So right now we see that there's no more message header. Now we're only taking in SOC, right? And this is a big function again. So this will get the linked list. It'll handle something called MTU probing, if you've heard of it before. It'll handle congestion control, and it calls TCP transmit SKB. So these are other features. You see like along the way, right, they have a lot of features in the kernel, and they kind of split it up to like, this function is responsible for this function is responsible. It's just a way of organization for the features. Probably in a logical way. Yeah, so now you call TCP transmit SKB, it takes in, so now they took the linked list and they pass it in here. So we're back to here, and this is just calling this. So I think you'll see a lot of things like that where they're, this guy and this guy. Like what's the point of this function, right? This guy is kind of useless. But I think the point of it is that sometimes as the API changes, right, people might want to attach like hooks, right? And then they'll actually insert more code here. So this is a way for like the upstream code to not need to modify this guy. If they call this guy, you can basically insert code like in between here without like changing the behavior upstream. So you'll see later that people do insert like eBPF stuff here.
What does eBPF stand for?
Extended Berkeley Packet Filter. So it's basically a way of like, it's a kernel plugin system.
Okay.
Yeah. So this guy, once again, we have a iNet connection socket. ICSK stands for iNet connection socket. So more indirection. And so more indirection, and we see this guy, right? So it calls IP local out. IP local out. So yeah, so I do not have I did not write this here, but IP local out basically calls IP local out again with 2 underscores. It calls dest output, sorry. Yeah, so dest output calls skb dest output. Another function, another indirection. And this just gets the entry. So it calls, so now we're at another place where now we are, now we're at another level indirection. DST entry, I do not have notes here for what it means, but I think it's something close to the nick. So yeah, so you see that we set over here, one of the fields we set output is this guy. So basically we're calling IP output. So what is IP output? Okay, that's where my notes resume. So IP output calls, it checks net filter for, over here it checks net filter for post routing. So if you guys heard of NF tables, right, IP tables or NF tables, they are routing rules. If you guys use like UFW before, the command UFW, it probably uses either IP tables or NF tables, and basically these are like firewall rules. So this is where your firewall rules are implemented in the IP layer, right? Yeah, so that's how firewalls work essentially. They hook into certain part, prevent packets to go out. And if this is okay, then it will call IP finish output. So yeah, we see how firewalls hook in here. And here's what I meant by eBPF. So this is where eBPF hooks in also. So I don't know, like hypothetically, if I ask you, do they check NF tables first or do they check eBPF? Then based on the code you just seen, right, it actually calls NF filter, the NF tables first, and then it checks the eBPF. So I guess it's useful if maybe you're writing eBPF code and you're not sure why am I not receiving it. Maybe you might want to check NF tables. Just an obscure use case, obscure hypothetical example where looking at the kernel code might tell you something that looking at other documentation does not. Okay, and yeah, so I think from here, okay, I'll just skip ahead a bit because it's not too interesting. But I think this function handles this function handles a bit of neighbor calling. The full detail you can read it yourself as well in the link there. But actually, at the very last stage, you call something called QDisc, which stands for Q discipline in the Linux kernel. And Q discipline, it has these two functions. So this is like the queue between your IP layer and what we call the link layer. So from here, that brings us to the end of the tracing. But basically, as you see that it just goes down with all the features, down, and it hits a queue, right? So yay. So below that, I didn't really analyze it, but I'll stop here because, I'll stop at this layer because I think below that is driver specific already. So if you are to modify anything, it might be a little bit difficult to modify the driver. So I'll just end the analysis here because this is basically the stuff that you can, this is basically the TCP and above, which you can kind of modify. You see there's a lot of bells and whistles, right? So if you're working at a HFT and want to like optimize latency, then you look at all these bells and whistles and you can be like, oh, maybe I don't need to check this setting, right? And you can just cut it out. And all the vtable indirection, function pointers indirection is very expensive. So you can, if you know the exact implementation you are going to use already, then you can probably cut it out as well. So you can kind of use this as a reference implementation for TCP as well, I guess. If you have to implement your own one in user space, for example, right? So if you tell the kernel, hey, I know what I'm doing, I'm going to implement TCP myself, right? Without all the bells and whistles, so I can optimize for latency. And then the kernel is like, okay, sure, here's a buffer that you can use to write to the NIC maybe. And that's essentially the idea of AFXDP, which is like kernel bypass for networking. So so this is an example of C-style inheritance. You see that this guy is writing a comment here to say that this guy, because TCP sock is essentially extending INET connection sock, he's saying like this guy has to be the first member, right? And you see how it's used is like it's just used as a pointer casting. So if you pass in a sock, it can be casted to a TCP sock by just casting the pointers. So if the thing you pass in here is not a TCP sock, then this is like undefined behavior. It's like really, really bad. But if it is, then it just casted. And then basically this is how we do C-style inheritance, which is pretty interesting. Okay, yeah, so I've covered the code. So I'll just briefly, this won't take too long. I'll just briefly go through like some of the networking concepts, hopefully to tie in with what we saw just now. So a packet is basically this thing that gets sent at the end. So it's kind of like an onion, right? If you're the application, you send some text data. Then as it goes down, as it goes through the many layers, the other layers will wrap this data with additional headers, right? So TCP header would, I don't know the details. If anyone wants, they can feel free to interject. But it wraps it with some additional data. IP will probably wrap it with the MAC address, I think. then this guy will probably wrap it with like, okay, I don't really know, but yeah, basically this is the OSI model, and
MAC address, it shouldn't be IP address.
oh, MAC address should be here, is it?
Yeah.
MAC address should be here. Okay, then I think this is the IP address, right? Yeah, I think that makes more sense. Yeah, and I think the TCP, is it a port? Is the port over here?
Yes.
Okay, yeah, port and yeah. Okay, so so this is the concept of a packet. Essentially, you have some user data, and how I append. That's how you see that I actually prepend. It's actually prepending the headers, right? So how do you prepend without making sure that you do not you still have space? The idea is that you actually have a headroom, right? You have a headroom here that says like, oh, I can use this headroom to expand and append more headers. And also likewise you have a tail room. I don't know what you put at the tail room, but I think I'll probably assume they put this thing at the tail room. But basically this is a struct. The struct has a head, data, tail, end, and length. And what's really cool is that so these are certain operations you can do on a SK buff, a packet, right? Put, push, pull, and reserve, and they correspond to these pictures there. This block is really good for explaining it. And so, for example, you can see that push, it pushes a header, right? So it just deducts from the length. The pointer reduces by length, and then the length increases by length. And then you have some sanity checks to make sure that you didn't exceed your headroom. Yeah, so this is pretty cool. I think it's like, you can see actually what is a packet, right? And actually the core packet is a very simple thing. It's just a chunk of memory. It's just what you put in the packet that is meaningful. So this is an example of how a packet is used. So for example, yeah, over here we see that we actually, so we see that here in this function, we call skb push, right? We make room for the IP header, and then we do reset network header to clear out the bits, I guess. Then we get a pointer to the IP header, which according to the one is just a casting, right? It just casts. So this is a pointer to the header that I can write to, and then now I see that I do some IP header fragmentation of TTL and protocol. Yeah, so I guess this tells you that IP header stores the TTL as well as the protocol, as well as the addresses, right? Yeah, so so it's pretty interesting that you can see like what actually goes into a header if you analyze the source code. Okay, so some concepts that I learned along the way. One of it is something called TCP segmentation offset, and basically the idea is that segmentation is very expensive to do for the CPU because you calculate checksums and stuff. So what you can do is you can just pass the network interface card a huge message, and then let the hardware do the segmentation. So that's what they mean by offload, right? You offload the segmentation to the hardware. So that's also a keyword that appears quite a few times in like discussions of kernel bypass. They always say like, oh, offload. And likewise for generic segmentation offload, we see that what if the user does a TSO, but the hardware actually doesn't support it? Then in this case, this guy will come and save the day. There's something called Nagel's algorithm. I hope the YouTube, I hope the YouTube commenting the closed captions algorithm doesn't flag it out. But basically, for small packets, example is telnet, right? If you send SSH, right? You SSH, then every key you send, right? Imagine it sends out 1 byte of data, and the headers itself like 40 bytes. So that's quite wasteful, right? So like the idea is you can accumulate the packets, and then you send them in a batch. So this is something that you analyze the kernel source code. It appears in one of the implementations. So like as you go down, some point there'll be like some mention of this algorithm, right?
How does the algorithm work exactly?
So the idea is actually quite simple. So if you see the Wikipedia, right, it's just it accumulates guys until it receives an ACK. Then it sends out until it receives an ACK from the client. Then it sends out the whole batch.
So when does the client send an ACK? Like?
So the idea is that you do not want a case where you send data, and every data that you send, imagine every one character that you send, you establish a whole new like TCP connection for it. So you call like SYN, like imagine you call one whole connection for it. So imagine you do like SYN, you call SYN with just 1 byte, and then you just send 1 byte with the whole TCP connection. You call SYN again, and you just send 1 byte. You just call SYN again and send 1 byte. The idea for this algorithm is that you send SYN with all the data you have so far, and then instead of just spamming new connections and creating new connections, you just accumulate them, and then once you receive an ACK, then you send a SYN. So it's like I don't want to do a SYN flood, right? I don't want to flood you with SYNs. I don't want to be like SYN. Then it creates many new connections. Instead, I just want to SYN and wait for you to respond first. Then I give you more data. It's a way of not like.
So the client responds when it receives the first packet, right? So basically, you hold the data until the client like confirms that they received data.
Oh, actually, this is from the perspective of the client sending the server. Sorry. So the client is the one that initiates connection. So this is like the algorithm
this works the other way around, right? With the server sending packets to the client.
I think the example they gave is for telnet, which is like SSH. So I am not sure how it works in a server context, but this is, I'm not super sure on that actually, how it works in a server context.
Basically, this algorithm waits for the server to respond first before you send your next.
Correct.
Data.
So that's just the idea.
That's just the.
Yeah, I think.
But I'm sure there's more complexity to it,
I
right?
think people in the 1960s or 70s had a very easy life inventing new algorithms.
Oh, okay.
Just come up with some, like imagine a linked list, right? The guy who invented linked list is just like, oh, let's just call it like Tom's algorithm, Tom's data structure. Like, okay, it's I feel like it's okay. I guess the guy who invented must have had enough influence to name it after himself. Yeah, it's quite a simple idea though. So there's another one which is called TCP delayed ACK, which basically it delays the ACK, and you can see that if I'm delaying the ACK, this is something that might interfere with the previous algorithm. So there's some papers on how these two interact with each other. Okay, so this is something that is not exactly networking, but my friend just told me about it. Basically, it's a paper that, you know how like if you do AWS now, right, a lot of right, imagine like the AWS, they need to run some kind of hypervisor to check like security settings. So basically, this paper implements the same security features that the Linux kernel provides, but it uses those features to implement essentially the same API, the same security guarantees. So you're not losing any security guarantees, but you're improving I/O by 80%. My friend said. Okay, so there's another thing that I was looking at, which is called receive side scaling. This is another feature that you see in the kernel. But basically the idea is that, this is more of the driver side, which I didn't really cover the code for, but the idea is that when you receive a packet, when you process a packet, you can use multiple calls to do it. And there's a lot of design decisions. The design space is quite huge for here, so I won't go too much into detail except to give you guys this link. But it's just another thing to take note of, I guess, if you want to learn about kernel features. Yeah, so with that, that's all the things I could cover. So I guess any questions from here? Yeah, that's all.